Welcome back. So in the last class we have started our discussion on EV motors and we have seen what were the requirement for an motor to be used in electric vehicle applications. Then we have started our discussion on induction machine, which was characterized by simple construction and robust structure, where we have seen its limitation. It was not as efficient as our permanent magnet synchronous machine, and we have started our discussion on PMSM. So it is an synchronous motor. It will rotate at the synchronous speed. So what is synchronous speed? It is 120 F by P, where F is the supply frequency and P is your number of poles. So it is an magnetically fed from the rotor side. So it will not have any type of brushes or slip rings in the rotor structure, as we have seen for our the induction machine. In the induction machine, we had the short circuit on the rotor end circuit, and there was some current which was flowing through the path. Whereas in this case, no such case will be there, because rotor already has an permanent magnet which will by default produce your required working flux inside the machine. And lamination rotor core common in NM, it offers exceptional efficiency and high power density. Okay, so it does not require any type of rotor copper inside the structure, so the losses are also eliminated. So because of that, it will be having higher efficiency and power density. So what is the importance of this power density? The size of the motor will be very less compared to the other options, because it will be much compact, because the rotor does not require any external supply. So I can pack it very in small size, so which is more important for our electric vehicle applications. So they are used in other various types of applications. The application of interest as far as is electric vehicles. Now, inverter-fed PMSM type. So generally, whenever we place the PMSM inside an electric vehicle, so we require it to run at variable speed. So how that will be done? It is always done by using an inverter-fed PMSM. Okay. So similarly, if we have induction machine, that also will be fed from an inverter circuit, because our battery bank is DC. Then from this variable battery voltage, we will be changing it to a fixed DC by using a DC to DC converter. Then the second stage of conversion will be from fixed DC to an AC output signal. Okay, so that will be an inverter circuit in the normal operating principle. When we are going for 4-quadrant operation of the drive, may it be induction machine or PMSM, we can have some type of regeneration. Okay, so back flow can be occurring. During that mode, it will be operating in the rectifier mode. Okay, so but most of the time it will be in the inverter mode of operation. So what will be the characteristics required by the inverter which will be feeding this PMSM? So it will be having a variable frequency drive. Okay, so why it requires variable frequency? Now we have seen that the motor runs at the synchronous speed. Now we have to change the synchronous speed if I require to change the speed of rotation of the vehicle, which acts as the brain and power supply for the PMSM, and it cannot be started by connecting it to the fixed frequency AC. Why? We have seen that it will be magnetically locked, or it will rotate at the synchronous speed. Suppose directly we apply the 50 Hz, so the speed of your magnetic field will be very high, so it will not be able to track that speed. So there are various options to make it start or make it come into operation. So we'll see those. Okay, so now inverter takes a direct current from the power supply and converts into three-phase supply. In our electric vehicle applications, we generally restrict our motors to three-phase. We can go for 5-phase and those things for spacecraft and those things, but for our electric vehicle, most popular is our three-phase architecture. So it uses any type of active or fully controlled device, that is your IGBT or MOSFET. So what is meaning of fully controlled device? We have seen that during our discussion in the converter study. So when I say fully controlled, so it will be turning on and turning off by using the gate signal. So this will be operated by using an PWM board and the technique we want to implement. So the PMSM can be run in very different methods of control. Classical control, and we have vector control also, where we will be going for decoupled frame. So which also we have seen in brief while we were discussing our converter topic. So here it will be synthesizing a variable frequency and variable voltage AC signal, which will be sinusoidal in nature, because our AC is generally considered as sinusoid in nature. Okay, so it will be operated at variable frequency and variable voltage. Why it is so? To vary the speed of the motor, so that the vehicle can rotate at different speed. Now here when we go for your electric vehicle applications, so this will be the primary drive, or it will be the main force which will be generating the torque required to move the vehicle. PMSM serves as the main proportional engine in most of our electric and hybrid electric vehicle. Also we find this PMSM machine because of its better characteristics compared to the induction machine. Only limitation of this one will be the cost point of view. So it will be through an gearbox or through an direct drive configuration based on the application of the vehicle or the range of speed we are trying to target. We can have a single speed reduction gearbox. So what is the meaning of this one? The gearbox will be coming with a fixed ratio. We will not be having any clutch to change the gear by the user. It will be fixed by the manufacturer, or it can be directly connected without any gearbox as per the application or as per the design specifications. Field weakening region utilization. So in this case, if you see in the induction machine or the other machines, how we are going into field weakening mode, because it was excited from an external source or we were depending on electromagnetic induction, whereas in this case we have a permanent magnet. So how we are able to operate it in the field weakening mode? We will be opposing or introducing an opposite magnetic field such that the rotor gets slightly demagnetized, temporarily slightly demagnetized, so that we can go for higher speed. Okay, so while discussing our induction machine, we have seen when we go into the field operating region of operation, our speed of motor will be increasing beyond its rated speed. So for those type of, when we are in the highway where we want very high speed, when we go, the internal back EMF is nearly equal to the battery voltage, or we have reached the rated voltage, then we will intentionally inject an negative d axis current such that our permanent magnet slightly gets demagnetized and we go into field weakening mode and we achieve higher speed. Okay, so this comes with a cost. If you go for repeatedly magnetizing it, it can get permanently demagnetized, whereas in this case we assume that it is temporarily demagnetized, and when we remove this negative excitation, it should come back to its original magnetic state. Okay, so packaging and space are constant. In electric vehicles, our motor should be as compact as possible because it will be moving with the vehicle and it will be occupying some space. So in this case, the most volume consuming component in the electric vehicle is our battery pack. Because of the technology and the required range and voltage, we cannot optimize it further. We will be having some particular size. So now here we get an additional advantage when our PMSM is used, that is, it will be having a smaller size. So we will be having a compact design so that more space will be left for the vehicle user. Thermal integration, in this case there is no rotor side losses associated, so it can be made very compact because we do not require any type of heat evacuation from the rotor circuit. It has to only cool the stator side of the circuit majorly. So it is compatible with our liquid cooling jacket, so which will be having an better efficiency in terms of the space. So we will be able to make it highly compact, or we will be occupying very less space when we go for PMSM based electric vehicle design. Okay, so now let us see what are the advantages and limitation of this PMSM. So this is having an exceptionally high efficiency because the rotor side losses are completely eliminated. Now we have an permanent magnet inside it, so there is no external supply which is being given to it. So the rotor side losses are completely eliminated in this case. Superior powertrain and torque density, we have seen this in the last slide. Because of the compact structure, its power density or the torque density will be higher, or it will be occupying an less space on the electric vehicle. High starting torque, so this is one more advantage. During the starting, we know that the inertia will be high or the vehicle will not try to move, so we have to apply a higher starting torque which is available with our PMSM. Excellent heat dissipation, this also we have seen. So because of the compact structure and better compatibility with our liquid cooling system, so it will be having an excellent heat dissipation and we can have a compact system while we go into the PMSM. So precise dynamic control, so this dynamic response will be better when we go for our PMSM drive. Then everything comes with some type of limitation. So what will be the limitation of our PMSM? First is high manufacturing cost. So we have discussed this multiple number of times. Because of the use of our permanent magnet, so its cost will be higher. Risk of thermal demagnetization. So we have seen that the permanent magnet, it can be demagnetized because of various factors while we were initially discussing about the permanent magnet. So that risk is present with us because we have a permanent magnet on the rotor circuit. High speed back EMF hazard. So we have seen that during high speed operation we will be slightly demagnetizing the rotor circuit, so that can produce some type of long term effects on the permanent magnet. Supply chains vulnerability, because we do not have any resources of rare earth material, plenty of them are from the imports. So this is a major concern when we go into the PMSM. Then complex control requirement. This is not a self-starting machine. Okay, so how it will be started? So we will be going for a slow ramp up, that is we will be increasing the frequency slowly, so that we directly do not go into, suppose 50 hertz apply, that motor is rated for 50 hertz, then directly we do not apply 50 hertz, we will be slowly ramping it. So this is one way of starting our PMSM. So what will be the other way of starting off the PMSM? We can have an position sensing system, that is our absolute encoder, which will be giving us the absolute position of the rotor circuit, or the other option is we can have resolver. Resolver is an advanced version of our encoders, which will be directly giving us the position of the rotor. So why this is important for us? So when we supply the source, AC source, for the first time, if I know where the north pole or the south pole of the rotor is located inside the machine, or at what point I have stopped the vehicle, so I will be directly applying the AC voltage such that an opposite pole is developed nearby that, and an torque is generated and our rotor starts moving. Okay, so because of that we will be requiring the absolute position or the actual position of my rotor circuit. So because of that we will be having an complex control design. So there are two options: either we go for ramping up the frequency, that is frequency will be slowly increased so that the rotor will be slowly catching up the speed, and the second option is we can have some position sensing and we can directly start the vehicle. Okay, so based on the cost and other design factors we will be choosing any one of them. So the control complexity will be bit higher compared to the induction machine, which is self starting machine. So in that induction machine we do not require any type of position sensing requirement, because it is self starting. The moment we connect an AC supply, it will start rotating. Okay, so in this induction machine, why we had slip frequency, whereas in this case why it rotates at the synchronous speed? Because here we have double excitation, that is on the rotor side we have a permanent magnet which is creating the field, and on the starter side we have supplied with an AC or an variable. AC is nothing but an variable supply, it will be having positive and negative half. So because of that we will be creating a rotating magnetic field, and the other field will be coming from the rotor side of the circuit, and the interaction of these two fields will be giving us a force inside the circuit. So in induction machine, why it was slightly below the NS? Because if suppose this is my NS speed, now I am going for induction machine case, so my rotor will be rotating at Nm. Suppose this is the slip times of my Ns, which we have seen. Now here how this gap will be filled? Our frequency will be introduced on the rotor circuit. What is the meaning of that? The AC which will be generated in the rotor circuit will be having an frequency such that the speed between the suppose I mark the fly S at the speed of my starter circuit, phi m will be exactly aligned across the axis. This gap will be filled by the variable frequency which will be introduced in the rotor side of the circuit. Whereas in my PMSM drive, now the NS is at an fixed speed because of my fixed supply frequency. Suppose I have applied the rated frequency, so it will be running at a fixed speed. Now my rotor will be rotating at that particular speed such that both of them are aligned. So if both the magnetic fields are at the same speed, then only we will get some type of torque production, that is the mandatory condition. So in our synchronous machine, so as we have an permanent magnet on the rotor circuit, so it should rotate at that particular speed such that the relative speed between both the fluxes becomes zero, and torque can be produced. So this is why we have some slip in the induction machine and we do not have any type of concept of slip in the PMSM. It rotates at that particular speed. Okay, and induction machine, it is self starting. whereas this is not self-starting. We will be having either frequency ramp up or we will be having some type of position sensing. So these are the merits and demerits of our PMSM drive. Now let us see the next machine which will be used in our electric vehicle application, that will be our switched reluctance motor. Okay. So as this name suggests, reluctance. So this operation of this machine is based on the reluctance principle. What is the reluctance? It is the equivalent of electric resistance. Okay, so when I go into the electric circuit, I see the definition of resistance, opposition of your flow of your electricity. Similarly, reluctance is nothing but opposition to flow of your magnetic field lines. So it is a doubly silent electrical machine. So what is the meaning of doubly silent? The air gap will not be uniform on both the starter and rotor circuit. We will have some type of silency inside that. Okay, so when the air gap is not uniform, we say it to be an silent type of configuration. So on the both on the starter and rotor, we will have silency in this case. So that's what it is called as doubly silent electrical machine, that produces torque because of the tendency of the rotor to move towards an minimum magnetic reluctance path. Okay, so the main operating principle of this one is the reluctance tendency of a magnetic material to align itself towards a minimum opposition path, that is minimum magnetic reluctance path. Okay. So unlike conventional motors, the rotor neither has a permanent magnet nor it has winding. Okay. So when we have started our discussion on induction machine, where we had slip ring as the popular configuration, where we had rotor bars which were short circuited at the end terminals, and because of that we got an variable frequency of induced EMF in the rotor circuit, and because of the interaction of the rotor and stator field, we have got some type of force, the torque which was generated. Then to eliminate the rotor side losses, we have seen the PMSM which was having compact structure, and we had permanent magnet on the rotor side. Now in this case we will eliminate both of them. Neither will have any type of permanent magnet on the rotor circuit, neither it will contain any type of winding or copper rods, or any arrangement will not be there. It will just be a simple magnetic material which will be placed on the rotor circuit. So because of that, it is simple, robust and cost effective. Now we are eliminating the permanent magnet, so now we are no longer dependent on the rare earth materials. Neither we have some type of complex construction principle, because the rotor head is just an magnetic material, so which will be easily available. So it is simple, robust and cost effective. Now the permanent magnets have to be inserted inside the machine when we go into the PMSM drive. When we go into our induction machine, rotor bars has to be designed on the rotor side, because squirrel cage is the one which will be popular for our electric vehicle application. There we will have rotor bars. In this case, when we go into switched reluctance motor, both of them will be absent in the circuit. So SRM is one of our simple electrical machine. It contains only laminated steel. Okay, so the magnetic material which is popularly used to construct the rotor as well as stator will be your laminated steel. Okay, so it reduces, because these laminated steels are easily available with us, so its cost and your robustness, or the machine will be more robust in nature, because the laminated steels are very available from very long time, and technical know-how is already available with us. The growing concern of the rare earth material, why these rare earth materials were required to, because they were required to develop the permanent magnet, the PMSM drive. Okay. So now this, because of these key advantages, that no longer we require any type of rotor bars, or no longer we are dependent on imports to have the permanent magnets. So this has been selected as emerging as one of the electric vehicle motor. This makes the, what advantages we get, what imports is one of the factor. The other factors are low manufacturing cost, because we are using the readily available material which is not a new material, so the cost is also less, and it can be operated at very high speed and harsh environment like our electric vehicle, because the motor will be moving along with the electric vehicle. So for those type of application, these are very much suitable. So everything comes with some type of challenges. So what will be the challenges associated with this machine? nonlinear characteristics, torque ripple, and high acoustic noise and vibrations. Okay, so this will ambient noise will be somewhat higher in this case compared to the other machines. So we'll see each of these characteristics when we go into the details operation of this motor. So here we have another motor which is having similar type of operation principle, that is our stepper motor. So what will be the difference between the switch reluctance motor and the stepper motor? If you see the construction wise, operating principle wise, both of them will be having the same operating principle. So how they are different from each other? The main difference is the stepper motor is generally used for control application where the torque requirement will be very less, whereas SRM now in this case we are using it for electric vehicles, so where the torque requirement will be higher and the step size. Okay, so this switch reluctance motor will also move in the steps, which is dependent on the strokes which will be produced. So what is the meaning of strokes and those things, we'll see that shortly in the next few slides. So here the number of strokes will be higher, or it will be having an smoother movement. We do not want the electric vehicle to move in jerks, okay, or take some steps, certain steps, and then it will be causing inconvenience to the EV user. So in case of stepper motor, the step sizes will be higher, or it will be moving in jumps, whereas switch reluctance motor will be having a smaller step size such that it has continuous rotation, or the user will feel that the motor is rotating continuously. So let us see what will be the structure of our SR. As an example, here we have an 12 pole starter configuration, and we have an rotor structure. Okay, so here if you see double silency, what was the double silency? If you see the air gap on the starter side is not uniform, as well as on the rotor side also it is not uniform. Okay, and construction wise, what will be the advantage over here? So it is having silency on both on the rotor and in your starter circuit. Okay, so here we will be having concentrated winding. Okay, so while discussing our previous machines, we have come across the term distributed winding, and we have discussed that it will be necessary to eliminate the harmonic torques, or it will be giving a better performance when we go into distributed winding. Whereas in this case we get one more advantage, that it will be having concentrated winding. So what is the meaning of concentrated winding? It will be having the same slot. Suppose the one of the winding is placed over here, so it will be finishing at the same point. So it will be concentrated or located at one point in the machine, whereas distributed it will be running through different slots. So when we compare both of them, the construction wise, concentrated windings will be more easier compared to the distributed winding. So this is one more advantage of the SRM, that it requires concentrated winding on the starter side. Rotor side will only have the magnetic material, no type of winding is placed inside that. This is the final rotor structure, there will be no winding inside it. Okay, now these are the starter poles. Now whichever is our sections which are present inside the motor, we call them as the poles. So these are our starter poles, they are located on the starter side of the circuit. These are our rotor poles, which are located on the rotor side of the circuit. The rotor pole of an SRM is made up of ferromagnetic material. Okay, then the number of poles in the starter and the rotor are different. Okay, so it is not required that both the rotor and starter should have same number of poles, and it is an undesirable phenomenon. We never try to have same number of poles on the rotor and starter, because they can get magnetically locked. So what is the meaning of magnetic locking? So if I have, suppose I have same number of poles on the rotor and starter and they are perfectly aligned, so it will have minimum reluctance path. Now the motor or starter, they will not be able to detach from each other and will not have any type of motion. So we call that as magnetic locking. So we do not want that magnetic locking to happen inside the SRM, because they are meant for rotating or continuously producing the torque, or the rotor has to continuously move so that the vehicle can move. So this is one key thing which we have to keep in the mind, that the rotor and starter pole numbers should be different. Okay, so suppose now we have 6 number of poles on the starter side circuit and 4 number of poles on the rotor side of the circuit, then we call this SRM as 6 by 4 SRM. Okay, so how the SRM are named? They are named based on the number of poles present on the starter and rotor by circuit. When I say 6 by 4, one should understand that it will have 6 number of poles on the starter side of the circuit and 4 number of poles on the rotor side of the circuit. Similarly, second example, if I have an 8 number of poles on the stator side and 6 number of pole on the rotor side, I call that as 8 by 6 SRM. Similarly, 6 by 8 SRM, where we will have 6 number of poles on the stator side and 8 number of poles on the rotor side, it will be called as 6 by 8 SRM. Okay. Now, here in the example which we were considering to see the basic structure of our SRM, it is an 12 by 8. So, if you see, we have 12 number of stator poles and 8 number of rotor poles. If you count N1 to N8 and S1 to S12, so it is called as 12 by 8 SRM. Okay. So, here if you see the motor examples which we have considered, generally we have even number of poles. Okay. So, that is what is the meaning of even number of poles. So, generally we try to design the poles in pairs. So, general numbers which will be coming is an even number. So, can we have suppose 9 by 4 SRM, where we will have odd number of poles on the starter side of the circuit and maybe even number on the rotor, or maybe odd number. Is it an possible type of SRM? Can we have an SRM with an odd number of pole pairs? So, before going into the answer for this one, can we have this type of configuration in our induction machine or an PMSM? No, always the poles are in pairs when we go for our SRM, or sorry, when we go into our induction machine or PMSM. Whereas for SRM, it can have an odd number of poles. When we go into the operation, we will understand because of the presence of concentrated winding. So, we can have this odd number of poles, but that is not popular. Generally, we go for even number. That's what is the normal practice produced followed for the other electric vehicles, so motors. So, same is adopted. Although we can have odd number of poles for our SRM because of the presence of concentrated winding, each pole will be independent from the other one. So, in this case, odd number of poles can be feasible, but the popular ones are even number of pole numbers, that is 6, 7, 8, 6, 8, 10, 12 or so on. Okay. Now, let us understand how this SRM will be operating. Okay. So, this SRM will be operating when suppose we have this type of cutout section, and suppose assume that this is an cutout section of the same motor which we were considering as an example. In this case, we have an concentrated winding. So, what is the meaning of dot? The current is flowing out of the plane, whereas when I see and cross sign, it means that it is flowing inside the plane of the slide. Okay. So, here when I try to find out how I can find out where the north pole and south pole will be there, so I can just go for the right hand thumb rule, or where I can curl my fingers in the direction of current, where the thumb will be pointing my magnetic north direction. Okay. So, the same principle can be followed over here, and I will see that north pole will be established on the top end and south pole will be established on the bottom end of the starter slot. Okay. So, this is the cutout section of the starter which has a concentrated winding, and as we are discussing now, the rotor will not have any type of winding. It is just a simple ferromagnetic material which will be having some type of tendency to get magnetized under the influence of external field. Whenever there is an external field, it will try to get converted into an temporary magnet and it will establish and north and south pole. Okay. So, if I have this type of excitation, what will be the pole which will be introduced on the rotor circuit? We know that the opposite poles attract each other. So, suppose I have a north pole over here. So, what will be the effect of this one? So, now this south pole, north pole will try to align themselves along each other because they are having opposite in nature. So, they will be generating an attracting force, and the tendency of our magnetic field lines will be to flow through the minimum reluctance path or minimum opposition path, and in turn they two will be trying to align themselves. So, when we bring this rotor pole in the vicinity of the starter pole, the ferromagnetic material of the rotor pole sees an external field from the starter pole. Okay. So, the first case we will not have this north or south pole on the rotor circuit because it does not have any type of winding. Only we have supplied the field to current through the starter side of the coil. So, it will be producing a magnetic field based on the sense of the winding and based on our right hand thumb rule. Now, it will induce the magnet on the rotor circuit and they will try to align each other. So, the magnetic domains on the rotor will try to align themselves in the direction of the external electric field which they are now seeing. So, in turn we will get an establishment of magnetic pole, and ultimately our rotor will get magnetized. So, the magnetic dipole align themselves in the direction of the field, and the ferromagnetic material will be developing an stronger and stronger magnet, and because of that we will generate an force or tendency of them to align themselves such that reluctance becomes minimum, or the flux can easily flow from the rotor side of the circuit to the stator side of the circuit. This is the basic of operation of our SRM. Okay. So, now as we continue this, suppose my rotor has been aligned, now I will go for the next load and I will try to excite it such that again it will introduce another type of attraction force, and when I repeat this task throughout all my starter slots, that is cyclically I will be exciting one of the or more than one of the coil sets, and I will be removing that and I will be exciting the next set, so that my torque will be continuously produced in one direction. Generally we consider the counterclockwise direction or anti-clockwise direction as the positive direction of rotation of the machine. This is the general use direction of rotation as positive, or we consider counterclockwise rotation as positive. It is not mandatory. We can design a machine which can be rotating in the clockwise direction, but the popular one is counterclockwise direction is considered positive. So, here if you see the rotor is moving in the counterclockwise direction, how this will be continuously moving. Now, the background principle is we will be continuously exciting or appropriately exciting the starter slots. Okay. So, this brings us to an concept or requirement to understand an concept, that is which coil will be excited in what sequence. So, that will require us to understand what will be the number of phases or how the phase of the machine is decided. So, we have seen the name of the machine, it is based on the number of rotor and starter slots. Now, we do not have any information about the phases, 3-phase machine, 5-phase machine, how we will decide that. So, we will see that. So, before that we require one more definition, that will be our pole pitch. Okay. So, what is an pole pitch? So, this will be given by, we can define the pole pitch both on the rotor and stator side. The first one is for the rotor, next one is for the rotor stator. So, based on the number of poles on the stator or rotor, our pole pitch will be defined. So, how it will be defined? It is 360 by the number of corresponding poles. So, for the rotor we have to divide it by the NR, or the number of poles on the rotor circuit. Similarly, for the stator we have to divide it with by NS, the number of poles on the stator side of the circuit. So, center position of the rotor or the stator poles are obtained from successive multiples of their respective pole pitches. So, what is the meaning of that? Suppose I have identified the pole pitch number by replacing it by 1, then I have to replace it by 2 to find out the next central or generally we consider the center point as our reference. So, just after one pole pitch apart, I will have the next center point of my next phase. Okay. So, that is what is the meaning of this pole pitch and how it will be used in the SRM. In an SRM, the electrical angle will be given by predict variation of the magnetic reluctance between the stator and rotor pole. Okay. So, what is this electrical angle? So, we have mechanical angle and electrical angle now. So, here we are discussing about electrical angle. So, let us understand what is a mechanical angle. Mechanical angle is nothing but a fixed angle in the space. Okay. So, always mechanical angle is restricted to 0 to 360 degrees, whereas electrical angle can be higher than that. Okay. So, how it is defined for normal machines? So, our theta electrical will be your P by 2 into theta mechanical. Okay. So, based on the number of poles, I can have the corresponding electrical angles. If I have more than 2 poles, my theta electrical will be more than 360 degrees. So, what is the meaning of that? It will be completing more than one cycle. The moment the rotor, suppose N1 is considered as the reference point, the time N1 comes the same location in the next cycle, we will have many cycles of the electrical AC. So, what is the meaning of that? This is my one AC cycle. Okay. So, if when the mechanical angle is 360 degree, I can have many number of electrical cycles in between. So, that is how it depends on, or how the electrical and mechanical angles are related with each other. Okay. So, we will stop at this point in this lecture series. We will continue from this point So what we have seen today, so we have started our initial discussion with the PMSM. We have seen its merits and demerits, and it was not a self-starting machine. Because of that, we required advanced control technique, and we have seen the limitation because of the presence of PMSM. Then we have started our discussion of SRM, where there will be no requirement of permanent magnet, or there will be no requirement of any type of conductor on the rotor circuit, and we have seen some basic operation and definitions related to SRM. So we will continue from this point in the next class. Thank you.